1, 2.
Man, I can't whistle.
You
I
need a
can't.
sound effect for ether flutes.
We do. There we go.
Ether
Perfect.
flutes assemble.
Hey everybody, welcome to Reading Night. Tonight we're gonna watch a couple videos. I think here we're gonna read a couple papers. Tonight we're gonna talk about the Sagnac effect, but it looks like we're gonna look at some matter wave interferometers, quote unquote. Change things up a little bit. The as typical on Monday nights, or used to be Thursday nights, whatever night reading night is, the disclaimer here is that reading night is about reading and research, and this is us literally reading live, researching live. And we may go off on random tangents. We may stop and talk about something for 2 hours and not get through the chapter we're reading, or we may read 3 chapters and it may be really boring for you. And that's okay. You don't have to stay if you don't want to. But if you want to come join us, if you want to come read with us, come join the Discord. You can find us on ethercosmology.com, or you can actually join the discussion directly there on Ether Cosmology, although we do these reading nights here on the Discord server. So there you go. There's the disclaimer, but feel free to listen in if you're interested. If not, we'll catch you on Tuesday nights for presentations, and we'll catch you on Thursday nights for live Twitter X Spaces. So there you go. Back over to you, Alan. I think we can go ahead and kick this video off. Did you want to give it any kind of context or anything?
Yeah, absolutely. So last night I was, brushing up on my Sagnacs, as one does, and I came across an interesting paper where they said they were measuring, Earth rotation with neutrons, right? Which is, very fascinating. So I was reading through that, looking into the setup they got going on to get a better understanding of what's going on. I found that it was awesome. That there's all kinds of interesting stuff in here about Bragg's diffraction and all this different stuff that they do for X-raying and imaging and different types of interferometry that can be done. So anyway, I figured we'd take a look and see what's going on in the electron or in the neutron neighborhood. So we'll start off here with this video on Bragg diffraction because this paper that we're going to be going through, they're going to be mentioning some new terminology here that I don't think anyone's ever heard. I know personally I never heard of it. So anyway, without further ado, we'll get into it. This is going to be very significant to what we're reading in a few minutes. Here we go.
What we're going to look here is Bragg's angle, or not Bragg's angle, but Bragg's diffraction. Now, I'll just show you this because I have seen a question in scholarship come up with this sort of thing. And what it's about is about X-ray diffraction. When we shine an X-ray onto a crystal, what we're going to get is a type of scattering. So obviously the X-ray hits these charges and these atoms that are in the crystal and are scattered. But we're going to have certain angles where they're scattered in phase. And the ones off the top plane of the crystal, this plane, okay, come down, we get this scattering. There's going to be a plane lower down in the crystal where we'll also get that scattering. Now, at certain angles, relative to this depth thing here, we're going to get a constructive interference. And Bragg's formula works out being, now if we chop that down there, chop that down here, so that's the same length here. So we've got D times the sine of theta, or 2D sine of theta. D depends which angle we're talking as theta. In this case, I'm looking at this angle being theta. So if that angle is theta, then in our little diagram here, the theta is this angle here, right? So we can say the path difference, which is this distance here and this distance here, so it's there to there, the path difference is going to be equal to D times the sine of theta. So D sine theta equals the path difference. There's two of them. So D sine theta, when that equals a whole wavelength, so we'll call that M wavelengths or N wavelengths, then this reflected ray is going to be in phase with this ray. So the ray off this plane of atoms, are going to be in phase at that angle, and we'll have constructive interference with that wavelength. So this is called Bragg's diffraction, and it's used in X-ray crystals. And this is always going to be the relationship between two planes. That's all there is to it.
All right, cool. So they say that they use that to measure the distance between, the atomic structure, the atomic structure and stuff like that. So it's very interesting. But that's how it works. They send X-rays into a crystal prism, or to a crystal plane, and they when they come back in phase, we're going to see how they can make use of that with an interferometer. But anyway, very cool stuff. So with that, we'll get into the PDF now.
I don't know, man. That to me didn't look like diffraction at all. That looked like a composite effect between reflection and refraction. And he didn't show any
So
refraction at all after the incident. You know what I mean?
yeah,
From top.
that was a really simple diagram just to show the angle stuff of it. Like the setups that you'll see, they diffract.
Hmm.
I promise there's diffraction.
I will suspend disbelief for now. Okay.
Okay. All right. Here. All right, we should be good now. Yeah. Okay, so this is Neutron Interferometry by Samuel A. Werner. Diffraction effects at wavelengths on the order of angstroms have been known since Max von Lau's demonstration of X-ray diffraction in 1912. Interference between well-separated coherent beams, however, is a much more difficult task to arrange. In 1965, Ehrlich Bonzi and Michael Hart of Cornell University were able to obtain interference effects between the beams of the X-ray with a wavelength of about 1 angstrom, initially separated by about 1 centimeter. They used a perfect single crystal of pure silicon to split the X-ray beam into 2 coherent parts by Bragg diffraction, and then further used Bragg reflections to recombine the beams. When they were varied in optical paths of the X-ray, one of the beams, they found an oscillation in the intensity of the recombined beams. This remarkable achievement opened up the field of interferometry to the region of the Armstrong wavelengths and raised the question to whether one could use the same principles to obtain interference effects between coherent beams of thermal neutrons, which are diffracted by crystals in the same way as X-rays. That's one thing I was going. Oh yeah, so the angstrom units here. So the wavelength size that they're dealing with here is 10 times 10 to the minus 10. So it's like the smallest wavelength that they, have ever dealt with.
Hey, real quick, is anyone else in the chat? Is Alan's stream blurry for you?
Yeah, totally.
Okay, so it's not just me.
Oh,
Same.
It was fine for the
Exactly.
video, but for this, it's kind of blurry. So I pulled mine up. If it doesn't, mine might look better on your end. So
Yeah, you just want to open it up, and I'll just read off of yours.
that works for me.
I don't want it to be shitty and out of sync and have different, well, we change streams now or whatever. Okay,
yeah, cool.
let's see here.
I think you were right around here, right?
Right here at the top. Yep. Well, Helmet Ranch, or Ranch, as some people know him. I don't know if anyone knows him as that. But
Roush.
anyway, Roush. Oh, thank you, sir. Wolfgang
Yeah,
Tremer.
Roush.
And what's this Bonds guy's name?
Trimer. Bonds.
Trimer.
False.
Bonds. Okay, thank
Bonds.
you. So Helmet, Roosh, Wolfgang, what was it again? I don't care. And Bonds.
We got
Time
Helmut
demonstrated-
Roush, Wolfgang Trimer, and Bonds.
Thank you. The boys. Okay, so demonstrated neutron interferometry in 1974 in a series of experiments at a small reactor at the Australian Atomic Institute
That's
in
the
Vienna.
Austrian.
Austrian, is it? Thank you, sir. Yes, it is. All right, an earlier attempt in 1968 by Heinz, Mary Leibniz, and Tazo Springer to construct the neutron interferometer based on the diffraction by the slits of subsequent deflections by a biprism proved to be only partially successful. Obviously, the principles upon which neutron interferometry are based are very different from those applied to optical interferometry, in part because we are dealing with a much smaller wavelength, and in part because we are dealing with neutrons. For these short wavelengths, one generally uses Bragg reflection from the crystal planes to split and recombine the beams to ensure the coherence of the recombined beams. And the crystal must be large enough and almost perfectly free from lattice imperfections. Obviously, it is not
See, he
possible
calls
to
it Bragg reflection right back there too, right?
Yeah, there's reflection, diffraction, and like you'll see it when you see the diagram. I promise. I promise there'll be diffraction somewhere. Okay, so see, obviously, it is not possible to polish and align the optical surfaces to fractions of a wavelengths. In this case, the fractions of an Armstrong, as one does for visible light. However, the use of Bragg reflection in the sections of the large in sections of the large perfect crystal circumvents this difficulty and permits the observation of interference between the two beams. With neutron interferometry, the phase of the neutron's wave function psi becomes directly accessible to measurement, whereas earlier only the amplitude, or rather the probability density, the absolute value psi squared, is directly measurable. So what he's talking about there is in the interference patterns when they were doing the readings before, like whatever method they were using, it was like kind of blurry. You couldn't distinguish the distance between the fringes very clearly. In this new method, it's spot on. It's the same as like the optical kind. So like, oh, cool, we can do this. So since 1974, a number of experiments have been carried out to use the Bond's-Hart type of interferometer to probe the phase of a neutron wave function. Figure 1 shows the interferometer and the typical experimental arrangements. Among these experiments have been demonstrations of the effect of Earth's rotation and gravitational field on the neutron phase as predicted by Schrodinger's equation, measurements of the neutron nucleus interaction potential, demonstrations of a fermion wave function reverses its sign after rotation by 2 pi, and it is only restored to its initial phase by a rotation through 4 pi. So it has to do a 720 to be in phase instead of a 360. So searches for nonlinear variants of Schrodinger's wave equation. In Article 1, I will give an overall review of the experiments in an attempt to convey the beauty and simplicity of this technique in probing certain fundamental aspects of quantum physics. I will also speculate on future experiments to give some flavor of the scope of new applications. A neutron interferometer. Various schemes have been proposed and to some extent realized for obtaining interference between effects between spatially separated coherent thermal neutron beams with having a wavelength in the Armstrong range. I will limit myself here to consider the sort of arrangement shown in Figure 1 and schematically depicted in Figure 2.
Sorry about that. So yeah, you're right here.
You're good. You're good. The interferometer consists of 3 identical perfect slabs of silicon perpendicular to a set of strongly reflecting lattice planes, typically the 220 planes. Slabs are machined from a single silicon crystal to ensure the perfect alignment of the crystal planes from slab to slab. Distances between the slabs are usually a few centimeters and must be equal to within about 1 micron. Dude, 1 micron plus or minus no microns. Yeah, a nominally collimated monochromatic beam is directed from a source to the first slab of the interferometer, point A in Figure 2, where it is coherently split by Bragg reflection. The resulting beams are split by the second silicon slab in the region near points B and C. The central 2 of these 4 beams overlap in a region of point D on the silicon slab. The 2 beams are each partly reflected so that G and O, leaving the third slabs are coherent superpositions of the beams 1 and 2 that have been passed through the interferometer. If the beam traversing path 1 is shifted by a phase amount beta with respect to the beam along path 2 by some interaction that increases the optical path wavelength. It sounds a little absolute spacey to me. The intensity is measured by the detectors C2 and C3 will change. The expected intensity of these detectors are in the forms of this equation given by equation 1 and equation 2, where beta is the difference in the relative phase of the wave function between paths 1 and 2, and alpha and gamma are constants that depend on the incident flux, the crystal structure of the neutron nuclear scattering wavelength of silicon. Well, that depend on the incident flux of the crystal structure and the neutron nuclear scattering wavelength of the silicon. Equation 1 and 2 predict that the neutron current is swapped back and forth between detectors C2 and C3, and the phase beta is varied. Note that the contrast of the interference observed by the counter C3 is in principle 100%, while the contrast of I2 or L2 can never be 100%. Alpha is always less than gamma. One generally records with the output from both encounters to enhance the rate at which significant data are collected. Our graphs, however, will only show the experimental points from one counter. The detector C1 counts the neutron and the non-interference beam directed along the line A to C. It serves as a reference. Although the basic principle of this interferometer seems simple enough, we must remember that there are perhaps 10 to the 9 oscillations of the neutron wave in each path of its oscillations of the neutron wave on each of its paths. Thus, there are clearly very stringent requirements on the thermal and microphonic stability of the apparatus. It is necessary to isolate the interference from the vibrations of the reactor hall and maintain the thermal maintain an isothermal enclosure around it. Active vibrations is much more important for neutrons and X-rays because the transit time of a neutron across the interferometer, typically on the order of 50 microseconds, is much longer than that of X-rays, which travel at the speed of light. Interesting. Thus, for the neutron interferometer, if the wavelength of path 1 varies because of vibrations relative to path 2, it must, as by much as the fraction of the Armstrongs during 50 microsecond transit time, the interference fringes are wiped out. To preserve the Bragg refraction condition for a given wavelength, 3 crystals must be aligned with the Darwin width of the beams. Width is the angular width of the incident beam over which strong Bragg reflection occurs for neutrons. It is on the order of 0.1 seconds of arc. What was this guy's names again? Bonesy?
Okay. Boss.
Driving me crazy. Boss. I'm just calling him Boss now. Boss Hart achieved this alignment in a simple, ingenious way. They cut all 3 slabs from a large monolithic single crystal. As a consequence of the great advances in crystal growth techniques prompted by the needs of the solid-state electronics industry, it's possible today to purchase at a modest cost silicon crystals of the required perfection of the typical dimensions 5 to 10 centimeters from commercial manufacturers. Nice. The accuracy with which the surfaces of the slabs need to be polished is not as severe as might be anticipated. The reason for this is that the index of refraction of silicon, or most any other material, thermal neutrons, differs only 1 by a few parts in 10 to the 6. Calculations show that a step of 2 microns of a surface of 1 by 1 slabs cause a phase shift of about 1 over 100 of a fringe for 1.4 Armstrong neutrons. Thus, the requirements on polishing are very similar to the requirements for an ordinary optical interferometer. Finally, there's the question of the extent to which the incident beam must must be monochromatic. Because the interferometer is based on Bragg reflection, the oh, you want to take a look at the apparatus now? I think we're at figure 1 and 2.
Definitely.
So that one doesn't really help.
Yeah, it's interesting.
If you could pull up Wikipedia real quick, I'll send you the link. We could look at like a diagram of the way that this is supposed to function here. It'll be helpful.
Interesting.
Do a link here in a second.
Or do you want to just share it? Because
Okay.
I'm gonna have to reshare anyways.
Oh, gotcha. A quick gander over here. Actually, it's probably going to look all retarded though.
Oh, really? Let's see.
Hopefully
That's a
not.
good point. I didn't think about it. You could try it to maybe zoom in more. Dang, it's taking a while to even load up here.
Really? Oh, you know what? It might be because
your
I'm
output.
uploading. Yeah, I'm uploading a bunch of stuff to Telegram and streaming.
Oh,
little too
It's
much.
taking
definitely.
your bandwidth.
Yeah, that's definitely
Yeah,
what's
it's just a
going
little
on.
too much. Yeah, if you could pull it up,
Are you allowed
Alright.
to,
go over
are you
the.
allowed to pause the upload? If you could pause the upload and just restart it when we're done here later, you shouldn't, have to reline up your file.
Nah, I can't.
Control Z it. Well, yeah.
Nah.
Control
Not
Z
risking it.
FG1. I just
It's
send it
fine.
to me. Yeah, is it in the chat?
I did. Should be.
All right. Boom. All right, and now let me go ahead and stop sharing. And here. Let me know when
Nice.
y'all are in. So phase contrast.
Yep. And then just scroll down a little bit. We're going to look at 3 setups. What they're doing. So there's one. Then scroll down a little further. We'll see. So there's another one of how they'll do it. So when they get split, like it diffracts out of that, and it hits the sample or whatever, and then through the other, fractions or that are coming through, they get the superposition of that of everything, and then that top image that we were looking at is what they see. And scroll down a little one more. There's another pattern that's a little easier to see it. You can see it bouncing back. There you go. There's your Boss Heart interferometer.
Are you satisfied? Stone, do you see your diffraction?
Stone, are you satisfied? Are we diffracting?
Nope. Nope.
No,
We're not. We are reflecting and refracting here.
Reflecting and refracting. Why do they keep
Sorry,
calling
man.
it
That's just
diffraction?
what's going on? I
do they keep
think
calling
your
it
buddy who did the
diffraction?
video is a little confused.
Oh, you think you just said the wrong terminology?
Mm.
Word. Thank you for the clarification. We will continue.
That's where the truth comes from, man. We like it.
All right, go ahead and direct your
All right.
attention over. So we looked at the diagrams, and then I guess basically we're on the next page here now, right? Right here. Because the interferometer is based on Bragg reflection, the...
Oh, yeah.
Yeah,
The wavelength along the given trajectory must be defined within about 1 part in 10 to the 6. However, this
That's a
definition is Yeah, thank you. However, this definition is accomplished by the interferometer itself and not through the preparation of the incident beam. Thus, one can carry out the experiments with the beams, which have a delta lambda over lambda. This is on the order of 1% and can be provided by nuclear reactors with the standard techniques for producing monochromatic beams. For a complete understanding of the quantitative performance of the interferometers, one must analyze the diffraction from neutrons with the slabs of the perfect single crystals using the dynamic theory of diffraction.
He said it. He said it twice, but I don't see it on the diagram.
Okay, somewhere someone out there is diffracting.
We're going to get to that guy.
We're going to get to the bottom of it. Coherent scattering. The scattering for thermal neutrons by nuclei is S-wave scattering because neutron wavelength is much larger, has a much larger radius of a typical nucleus. Another way of seeing this is as follows: the angular momentum of the incident neutron mass speed is on the order of mv r sub 0, where r sub 0 is the radius of the nucleus, because nu is on the order of 2,200 meters per second, and r sub 0 is around 10 to the minus 12 or 10 to the minus 13 centimeters. The angular momentum is much smaller than Planck's reduced constant times the square of L times L plus 1, or L equals 1 or larger. Thus, only the S wave, L equals 0 component of the incident beam interacts with the nuclear potential. The outgoing wave is therefore a spherical wave of the form E IKR over R. The parameter B is called the coherent scattering length, and it is proportional to the strength of the neutron nucleus interaction. Total scattering cross section is 4 pi b times b squared, so that except for the factor 4, which is a quantum mechanic effect. Is it? So it's where Feynman diagrams are and they're playing around. We're just running amok. B is the effective radius of the scattering of the nucleus. For the repulsive potentials, B is the positive. For the attractive potentials, it is negative. Traditionally, one has determined the scattering length of the nuclei from the diffraction data of a single or from single crystals or from polycrystals. Some experimenters have also used mere reflections or refractions of neutron beams to determine scattering wavelengths or scattering lengths. These experiments typically have the precision of a few percent. The neutron interferometer provides us with a new and very precise technique for determining scattering lengths, sometimes to within 1 part in 10 to the 4, free from the usual uncertainties of the Debye-Waller extinction effects always present in the crystal diffraction experiments. Debye-Waller effect is the change in the intensity of the Bragg reflection due to the thermal motions of the nuclei. The extinction effect is the change in the Bragg reflection due to the absorption of the multiple scatterings. Over the past 5 years, a group of collaborators from the Austrian Atomic Institute in Vienna, in Vienna, and the University of Dortmund in Germany, have carried out a series of precise experiments at the Institut Lau Levine, Institut Lau Lavaux. Oh no, Lavaux. I promise. Oh, dude. All right, Law Lavaux. God dang it. So you're telling me it's not Lavaux? Listen,
Dude, I've told you it's not Lavaux.
There's no V.
It's gone. It's over. It's forever in his head. Is
from Grenoble.
Dude, I've been Paul Lavouing for months, dude. There's no way I'm going to undo that. But dude, I can't even see it now. Okay, so anyway, Paul Lagrange point and the in Grenoble, France, to measure the scattering lengths of the nucleus or the nuclei using neutron interferometry. The principle of the technique is straightforward. If one of the coherent beams traverses a sample thickness T and the refractive index N in the leg of the interferometer, not to be confused with the arm of the interferometer, then the two beams will differ by a phase of beta equals 2 pi 1 minus n times t over lambda, or lambda. See, when they recombine. Here, lambda is the neutron wavelength. The index of refraction is n, given by equation 4. Capital N is the density of the atom, so that the phase shift is proportional to the scattering of the length given by the equation below, which is beta equals nt lambda b. For solids, one can insert a slab of material in one of the arms and rotate it about its axis perpendicular to the plane of the interferometer, thus changing the effective thickness T and inducing interference oscillations in the counting rates observed in the detectors C2 and C3. For gases, one inserts a gas cell into one of the arms of the. That's funny. Arms of the observes. For gases, one inserts a gas cell into one of the arms and observes the interference oscillation as one varies the gas pressure. Figure 3 shows a few of the beautiful results that the Vienna Dormund group had recently obtained at the Institute of Stone. Hit me with a
Langevin.
Long van is kind of what it sounds like you're saying. Is that close?
Yeah, it's Langevin.
Longva. Okay. It's even worse than I
thought.
Langevin.
Yeah, V-I-N. Van.
I give up.
Like vino. It's like vino. Like it's almost like your van, man, but it's van. Langevin.
That's what I said. Long van. Your boy Lao Longvan. See, these experiments were performed with a gas cell in one of the interferometers. One can compute the density of the atoms from the measured pressure with the corrections from the known pressure dependence on the viral coefficients E. Larger scattering length, the more rapid of the interference oscillations. For example, in helium-4, the scattering length is 3.26 times 10 to the minus 13 centimeters, or 3.26 Fermi. Yeah, I like that one way better, 3.26 Fermi, with a precision of 1%. For deuterium, the scattering length is 6.55 Fermis, and the frequency of oscillation with an atom density is clearly more rapid. Scattering length for hydrogen is negative. This is known from other experiments, but the sign of the scattering can be determined in the interferometer experiment using the quarter wave plate made of, say, breaking it up into small sections is killing. Let's see, I'm looking at it.
Aluminum top, right?
Thank you, sir. For say of aluminum, 0.05 millimeters thick, for which the scattering length is known to be positive, in observing whether the intensity oscillation shift by the left or to the right by a phase of 90 degrees, and the graph comes in the form of figure 3, which will show us there. To calculate the scattering length from first principles, one must solve the problem of the interaction of the neutron and all the nucleons in the scattering nucleus. This can be solved exactly only for two bodies. That is, for the scattering. No way you said that out loud. All right. So this can be solved exactly for only two bodies. That is, for the scattering from hydrogen. There are some very useful results for the three-body problem, neutron deuterium scattering, and recently developments of the calculations of a few-body problem to allow a more fundamental treatment of the four-body problem. Ooh, we're up to four bodies now. We're getting it. So VF Katchenko and VP Lavosphere in Russia Lavosphere, thank you. In Russia have carried out a detailed analysis of the Faddeev and Yakubovsky. Let's see. Equations with a charge independent separation central potential. Separable central potential. Neutron scattering from helium 3 and from its tritium and neutron scattering from helium 3 and from its tritium and experimental realizations of the four body problem. In this case, helium 3 is a strong effective attraction exists in the state of the compound nucleus has a total spin of 0. It depends markedly on the details of the nuclear force because of the large cross section of the neutron absorbed by the helium-3. The measurement of the scattering length is quite difficult. However, because the group at Grenoble has carried out a careful neutron interferometry experiment and has obtained a reasonable agreement with the theory. They are currently involved in the measuring of the wavelength of tritium with the idea that they are gaining insight into the charge dependence of the nuclear forces. Nice. Neutron interferometer measuring the average neutron nucleus potential of the same through which one of the beam passes. Because the interferometer is very sensitive to small changes in the scattering length, it is also sensitive to the small changes in composition of the scattering material. Thus, for example, by comparing the interference pattern obtained from a metal sampling containing hydrogen with that pure form metal sample, the Grenoble group has been able to measure the hydrogen content samples of various transition metals to a precision of about 0.05 atomic percent sensitivity, competitive with the best analytical chemical techniques. Quantum interference due to gravity. In most phenomenon of interest in physics, gravity and quantum mechanics is not simultaneously at play, or do not simultaneously play an important role. However, the neutron interferometer is sufficiently sensitive to detect tiny changes in the phase of the wave function that arise from changes in gravitational potential energy. Let's see. Here at the University of Missouri Research Reactor, a group consisting of Jean-Louis Studenman, now at Iowa University, and Roberto Colala at Albert Overhauser, both at Purdue University, and myself, has recently carried out citation 4, a precision experiment whose outcome depends necessarily upon both gravitational constants and Planck's constant. Oh, no way. So preliminary experiments were carried out over 5 years at the University of Michigan. Figure 4 shows the overall setup of the Missouri reactor. The thermal neutron beam emerges from the reactor through a helium-filled tube. A pair of pyrolytic graphite crystals serve as a monochromator for the beam and thus double as the crystal monochromator. This double crystal monochromator allows one to carry out experiments at various neutron wavelengths. The direction of the incident beam is fixed along with the local north-south axis of Earth. We see that it is important in these experiments. We will see that this is important to these experiments. Got to be aligned with the old axis of rotation, eh? Right, scroll down a little bit. Okay, that's it. Okay, the experimental procedure in the experimental procedure involves turning the interferometer and including the entrance slit and the 3 detectors C1 through C3 about the incident beam as shown in figure 5. At each angular setting I, neutrons are counted for the present length of time, or for a preset length of time. Paths 1 and 2 each have a horizontal
You had it down from the 3 boxes.
Yeah, I was just looking at the pictures real quick.
Looking at the path links.
There you go.
Nice. So let's see. It's important to these segments and sloping segments. The average gravitational potential of the sloping segments is the same, but depending on the angle phi, the horizontal segment for path 2 will either be above or below path 1. The difference in Earth's gravitational potential between these two levels causes quantum mechanical phase shift of the neutron wave in path 1 relative to path 2. To calculate the phase, one simply uses the de Broglie relationship between momentum and the wavelength of the neutrons, where we have P equals Planck's constant over lambda, given by equation 5. I think there's a little more under that. Momentum depends on the height, z, of the neutrons because the energy is conserved, given by equation 6, where m is the inertial mass and mu is the gravitational mass of the neutron. E is the acceleration due to gravity, which Shane is absolutely not allowed to kinematically derive from anything except for mass attracting mass. In these relationships, it is straightforward to show that the phase shift is given by equation 7, where A is the area enclosed by the two beam trajectories. Thus, as we turn the interferometer through various angles I out the incident beam direction, always maintaining the Bragg condition, we expect to see oscillations induced by Earth's gravitational field in the output by the detectors C2 and C3. The result of the experiment carried out with incident neutrons of a wavelength of lambda equals 1.419 angstroms is shown in figure 5b. The contrast of the interference pattern dies out with increasing rotation angles because the interferometer warps and bends due to warps and bendies lights slightly under its own weight. The scale of the angstroms is that it's rotated at about its axis of the incident beam. Which is not an axis of elastic symmetry of the device. This bending effect also causes small change of the period of the main oscillations. These effects have been studied and quantitatively measured with the in situ X-ray. What does that mean, Stone? Do you know what that means?
It means in place on the unit. As in included. Gotcha. In situ means on site.
Okay. Thank you, sir. X-ray experiments in which the X-rays are directed along the same incident beam path and the interfering X-ray beams are observed as a function of the rotation angle by the effect of gravitational redshift on the X-rays over the distance involved in the interferometer is negligible. One consequently assumes that the phase shifts observed are due only to the bending of the interferometer. The frequency of the oscillation due to the bending of the as measured by the X-rays can be subtracted from the frequency of oscillations measured with the neutrons, leaving only the effects of the gravitationally induced quantum interference. They've carried out, dude, that's so crazy.
Like, yeah, right.
We have carried out the extensive series of measurements at the variation of the neutron wavelengths and the agreements. The agreement of most of our recent results of the theory is at 0.1% level. Nice, dude. That's like it's like Sigma 5 confidence, boys. You're getting up there.
Thoroughly reified.
This interference experiment demonstrates that the gravitational potential coherently changes the phase of the neutron wave function. Furthermore, Daniel Greenberger, City College of New York, and Overhauser have derived a result like the equation 7, but with m instead of m and mg for the situation when the neutron source beam splits and the interferometer have a uniform acceleration of little baby g. In comparing the experimental results, we have the theoretical results. We have used the neutron mass as measured in a mass spectrometer, and essentially M2 instead of the combined M and mg that appears in equation 7. Thus, the agreement of our experiment with equation 7 provides the first verification of the equivalence principle in the quantum limit. No way, bro. They're bringing general relativity into the quantum realm with this. That's crazy. 19. That's nuts, dude. Let's see. In 1925, Albert Michelson, Henry Gale, and Fred Pearson carried out the famous MGP experiment, a heroic experiment. That, dude, you know what's funny? So they're equivalencing principling right now, right? But they're about to reference MGP, which directly refuted the mass energy equivalence because they couldn't derive, the fringe shift pattern based off of Earth's, resting mass. Essentially, they had to use the gravitational mass, and they couldn't do it. It's funny that they're like, we're equivalent, and then we're going to reference this experiment that shows that's not real at all. Anyway. A heroic experiment designed to detect the effect of Earth's rotation on the speed of light. They constructed an interferometer in the form of a rectangle, 2,010 feet by 113 or 1,113 feet, and were able to detect a retardation of the light due to Earth's rotation corresponding to about 1/4 of a fringe, agreement with the theory of relativity theory. The French scientist Maurice Sagnac, or whatever. What do we say?
Sagnac.
Sagnac. Had demonstrated in 1913 that rotational motion, unlike rectilinear motion, can be detected, which, rectilinear definitely can be, with an optical path interferometer. The physical principle involved in the Sagnac effect is the fact that that they use this principle for the modern gyroscopes. Neutron Sagnac effect. Oh, no way. They're saying that, light obeys the Sagnac effect in this, whatever a neutron is, and they say that it was, slower than the speed of light, but for some reason it's also obeying the same effect. The neutron Sagnac effect. In view of the differences in the way the light waves and matter waves behave under coordinate transformations, it is not obvious that an analogous quantum mechanic effect should exist for neutrons. Because gravitationally induced quantum interference experiments is carried out on the surface of the rotating Earth, a non-inertial frame. The Hamiltonian governing the neutron's motion contains a term dependent on the angular velocity of Earth, given by baby omega, the angular momentum L, and the angular momentum L of the neutron's orbit about the center of the Earth. Wow. This term, baby omega times L, gives rise to the classical Coriolis cause. Oh, is that okay? Yeah, never mind. Coriolis force. Although the force has an exceedingly small effect of the changing the neutron's trajectory in the interferometer, its effect in the neutron phase is not small. Calculation shows that the phase shift in the interferometer due to Earth's rotation to be expected can be given by equation 8. So here, A is the normal vector for the closed area. Dude, it's like literally the same equation that you would derive this, the Sagnac effect with. So the magnitude of beta sub r is about 2% of beta g, or beta sub g, which should have been easily observable in the precision experiments described in the last section. The effects of gravity and rotation can readily be separated because the two phase shift change in very different ways. One changes in the interferometer's axis. The incident beam direction from the local north and south direction, in fact, as one seen from equation 8, beta sub r vanishes in the area vector is normal to the Earth's axis of rotation. On the other hand, if the interferometer's axis is vertical, the gravitational shift remains constant as the interferometer rotates because of the symmetry of the situation. Studenman, Kola, and I performed an experiment with a vertical incident beam at Missouri, measuring the phase shift as a function of the interferometer's orientation angle about the vertical direction, because because beta sub g remains constant. This experiment is a direct test of equation 8. The result is shown in figure 6. When the normal area vector A points east or west, the phase shift vanishes. And if it points north or south, the phase shift is plus 95 degrees or minus 95 degrees, respectively. This result is in reasonable agreement with the theory, which predicts it should be plus or minus 92 degrees. Let's see. When we began the experiment, we did not know the location of the north-south axis of Earth relative to the reactor hull. Because the building contains a great deal of steel and magnetite concrete, a compass is useless when determining true north. We finally solved the problem by no way. We just whipped out the telly. We finally solved the problem by using a telescope to sight the star Polaris outside of the reactor building, and then use precision surveying techniques to carry out the line of sight into the reactor hull, which is below ground level. Because of the results of the experiment depend only on the inertial mass of the neutron M1, and the results of the gravity experiment depend on the product of M1 and Mg, one can interpret the combination of the two experiments as independent measurement of inertial and gravitational neutron masses in a quantum mechanical experiment. Recently, Max Dresden and Chen-Ning Yang have given an interesting derivation of equation 8 by considering the phase shift of the rotating interferometer arising from the Doppler shift due to the moving source and moving reflecting crystal. According to the general theory of relativity, there are phase shifts of very small magnitude in addition to beta g and beta r, which become larger as the neutron velocity increases. In particular, there is a phase shift due to the coupling of the neutron spin to the curvature of space-time. These effects have been studied theoretically by Jiva Anandita of University of Maryland and independently by Leo Stoldovsky. That guy.
Studolsky.
Thank you, sir. Stolsky from the Planck Institute in Munich. Whether or not the experiments can be carried out with a velocity regime is an open question. Its answer will probably require new technology. Magnetic effects. The operator for their... Go ahead.
Yeah, it'll probably require some correct thinking instead, I think, would be...
Let's see. Forgot the last part I read, but wave functions for a fermion. Oh, yeah, the magnetic wave function of a fermion. Although this principle... Yeah, thank you. Although this principle is well known and is deeply embedded in quantum theory, it has not been directly tested before the development of the neutron interferometer. Nice, dude. An experiment to observe this effect with the neutron interferometer has been suggested in 1967 by Herbert Bernstein. 1975, nearly simultaneously, both Grenoble Interferometry Group in France and the group in the US performed an experiment. Anthony Klein and Jeffrey Opt, I don't know, later demonstrated the same principle very nicely using a novel Fresnel diffraction interferometer. Nice, dude. They're just dragging neutrons through material medium. I like it. Basic idea of the experiment is that after a neutron rotates of an angle 2 pi, the sign of the wave function changes, or in other words, the quantum phase shifts by pi. The use of the magnetic field to change the orientation of the neutrons in one arm of the interferometer and observe the resulting phase shift. The geometry of the experiment is shown in figure 7. If the neutron travels from a distance L through a magnetic field B, one expects this phase to shift by the amount given by equation 9. Here, the plus or minus signs for the spin up and spin down of the neutrons. Gn is the neutron's magnetic moment and the nuclear magnetons. All right, is the nuclear magneton, and m is the mass of the neutron, and m is the neutron mass. Putting into the numerical values, we expect that for the precession of 4 pi, or for a phase shift of 2 pi, we have the equation given down here for whatever that is, Gauss centimeter angstroms. And we show that in figure 9, data from the original Grenoble experiment, which the neutron wavelength was 1.82 angstroms, the graph clearly shows that the phase shift of 2 pi corresponds to the precession of 4 pi radians. The neutron wave function thus is indeed a spinner. In classical physics, of course, no such behavior is possible. Rotation through 2 pi exactly resorts to its original state. The nonlinear Schrödinger equation. Last year, Abner Shimony suggested that the neutron interferometer offers a sufficient sensitivity to test physical reality of nonlinear variants of the Schrödinger equation. See the Schrödinger equation, in which additional terms of the form f, the absolute value of psi squared, appears in the Hamiltonian. In earlier theoretical studies, these guys had concluded that unlike the linear Schrödinger equation, some of the nonlinear equations have solutions in which the traveling wave packets do not spread out in space with time. These nonlinear equations, however, allow us to retain many of our Am I at that one, or am I on the far right?
Top center.
Top center, thank you. Visual interpretations of quantum mechanical theory. In particular, the Bohr interpretation of the wave function, Galilean invariance, and the conservation of probability. Dude, got to conserve that probability. Therefore, they concluded that the function f should be logarithmic to obtain physically attractive relations between non-interacting particles. Thus, in the case of a single particle, Schrödinger equation they proposed a term in the form of equation 10 should be added to the usual linear Schrödinger equation. The length alpha need not be a universal constant, because changing its value is equivalent to adding a non-observable constant potential to the Hamiltonian. Energy constant B, however, must be a universal constant. Be a universal constant. Same for all systems. They estimate the experimental data on the Lamb shift Lamb shift in hydrogen. That B must be less than 4 times 10 to the minus 10 electron volts. Jiminy pointed out that merely repositioning an intensity attenuating plate downstream in the particle beam should cause the change in phase not predicted by the linear Schrödinger equation. Factor minus B ln times alpha cubed times the absolute value of psi squared. And equation 10 can be simply viewed as a small intensity dependent potential, because all potentials cause the phase shifts in the interferometer experiment. This one also should also. All right, a straightforward calculation shows that if one positions an attenuating plate first at the point of the beams of the interferometer, and then downstream at the distance L from that point, the integrated effect of the intensity-dependent potential on the neutron phase is given by equation 11. Because nu is the neutron velocity and alpha squared is the intensity attenuation of the absorbing plate, Clifford G. Shull and his collaborators at MIT, recently carried out 2 beautiful experiments to these ideas using 2 crystal interferometers, absorbing plates of lithium fluoride and cadmium.
It's cadmium.
Cadmium, thank you. I was adding some extra letters in there. They detected no phase shift. This experiment places the upper limit on the values of the fundamental constants of B of 3.4 times 10 to the minus 13 electron volts. A Fresnel diffraction experiment carried out by R. Galler and G. Klein in A. Zellinger at the Institute of I can't do it. But you guys know. Thank you, sir. Placed an even lower limit on the electron volt of 3.3 times 10 to the minus 15 for the value of B for their energy constant. This is more than 5 orders of magnitude lower than the previous than the limit previously inferred by the lamp shift data. Oh no! Speculations of future. Oopie! I made an oopie. I accidentally precisely measured my way out of quantum mechanics. Oopie. All right. So speculations on the future applications. In a field as new as neutron interferometry, it is, of course, difficult to predict the future. Over the past several years, a large number of back to the envelope ideas for experiments have been suggested. Back of the envelope, sorry. The International Workshop of Neutron Interferometry, which was held in Grenoble 2 years ago, at which time some of these ideas were put forward. In the way of a conclusion, we'll briefly discuss some of these suggestions. Quantum theory rests on the principles of Feynman diagrams in that redshift or lamp shift situation of superposition. Oh, no way, which states that psi1 and psi2 are possible states of a system, and C1 and C2 are arbitrary numbers, then C1 psi1 plus C2 psi2 is a possible state of systems. It is usually taken for granted that the coefficients C1 and C2 are complex numbers. However, it is possible to imagine a quantum theory based on quantrinos, numbers that form A plus
those are
1B.
quaternions. Those are mathematical expressions. Quaternions.
Oh, thank you,
Faraday
sir.
loved them.
Oh, I bet he did. Quaternions.
Quaternions.
Quaternion.
No, just spell quaternions.
Quaternions. Thank you. Okay, Asher. So let's see. Your boy Asher Perez has proposed a simple test to see if the neutron nuclear scattering links are strictly complex numbers or whether they have an additional dimension allowed by fucked it up again. Quaternion quantum theory. This idea is to allow two flat plates of two different materials, say A and B. Placing the material A in one leg of the interferometer will cause the phase shift, say delta A. Placing the material B in the interferometer will cause a phase shift of delta B. Placing both slabs on the interferometer beams will cause a phase shift of delta AB equals delta A plus delta B. If the neutron scattering links are complex numbers, however, if they have small I can't do it. Quaternion component. Delta AB will not be equal to A or delta A plus delta B. Furthermore, because they did every fucking sentence now is gonna be
They're out to get you, Alan.
Dude, come on, bro. All right, quaternions, dude. I can't, dude.
Quaternions.
Quaternions. That's what I thought I said the first time.
Yeah, you got it.
Oh, quaternions. Okay,
it's simpler than you think.
Yeah, do not commute. You expect delta AB not to be equal to delta BA. We should expect a difference if we interchange the order A and B with respect to the directions of the beam. It is obvious that the effects to be searched for are very small. Otherwise, that would have already been detected in the neutron diffraction crystallography. In 1853, Fazao carried out an experiment designed to measure the velocity of light moving through a fluid. The result was found to be in agreement with Fresnel's equation based on the elastic vibrations of a stationary ether. While now we know that the result, we now know that this result can be derived from the conventional Maxwell electrodynamic theory, and that it is therefore consistent with the theory of special relativity. Oh, dude, that's what they now know. I didn't know that before, but they now know that. That's cool.
The old now we know.
Yeah, it was super consistent with the material media ether being dragged with the material media as well to give a little velocity boost. But also, it's we now know that it's that it's special relativity. That's cool. Several people, among them Michael Horn, Stonehill colleague Anton Zellinger, and Anthony Klein from Melbourne, right, have suggested carrying out the analogous quantum mechanical Zhao experiment using neutron. Dude, that'd be awesome. Using neutron interferometer to measure the phase and the shift of the moving medium. In fact, experiments along the lines are under the way by the Grenoble lads. Of course, we think we know how to predict the results, but maybe we are overconfident. Richard D. Slates proposes.
That's Delat.
Oh, dude, is it really? I was way off.
Yeah, it's Delat.
Thank you. Richard Delat has proposed constructing a Michelson-type interferometer, repeating the Michelson-Morley experiment using neutrons. Greenberger and I have suggested that carrying out an experiment to measuring gravitationally induced quantum interference with ultra cold neutrons could give a surprising result. Because the neutron trajectory would no longer be uniquely defined, and the WKB techniques for calculating the phase shift fails in the limit of the zero velocity. If one could construct an interferometer that works with these very slowly moving neutrons, it is conceivable that it would also be useful in the precision search of electron dipole. Sorry, I got mentally sidetracked there. It is conceivable that it would also be useful in the precision search for the electron dipole moment of the neutron. There we go. Let's see. There's been considerable interest in recent years on coherent parity violate. Man, there's been considerable interest in recent years on coherent parity violations because this neutron particulates in weak interactions, which do not conserve parity. Do you know what he's talking about, Stone? What is that?
Well, that means the neutron participates in a weak interaction. That's the verb that you missed there, which don't conserve parity.
Oh,
you might expect in forward scouting neutrons. There's a weak polarity violating spin dependence. This is absolute nonsense. But okay, let them build.
Yeah,
You're almost
dude,
done.
Let him cook. We got 3 sentences. Yeah. Let's see. FC Michael and independently Stadolsky have estimated that the rotary power of matter composed of heavy atoms at the normal densities to be about 10 to the minus 8 radians per centimeter. This small rotation appears to be beyond the limits of sensitivity of the interferometers that we are now currently using. However, Gabriel Karl has suggested that the effect can be enhanced if the phase shifting medium is composed of twisting molecules. That would definitely help with a given sense of helicity. Yeah, if you have really good helical structure atoms,
where do we get these twisted molecules? I mean, we're not gonna take it.
With the with pulsed neutron spatialation sources on the horizon, it is clear that the energy dependence of the neutron scattering lengths through the epithermal don't tell me. Yeah, tell me.
Bright-Wigner, and that's epithermal. You got that one right.
Bright-Wigner resonances of many isotopes we will need to be measured. It's also clear that the future will be able to carry out experiments using both polarized neutrons and polarized targets, probably dynamically polarized, so that one can directly measure the scattering lengths for both the spin states. Neutron interferometry will be
Televised.
useful for these kinds of experiments. Finally, there is the possibility of using the two coherent beams available in the neutron interferometer to help solve the quote unquote phase problem in certain crystallographic studies. Although this possibility has been discussed for some time, it still appears to require levels of perfection that the sample crystals and stability in the sample position that are yet difficult to achieve. I have not attempted to be all-inclusive in mentioning the wide variety of new ideas which have come to my attention, but only to give the reader a glimpse of the exciting possibilities for the future experiments.
Oh boy.
Nice.
Wow.
There we have it, lads. X-rays
Yeah,
and crystals
and what
Earth
year
rotation.
is this paper?
Is from the 70s. Let me
It's actually
double check.
1980. I just found it. It's in the title of the paper. It's in the file.
Oh, in the 80s.
Yeah, it's in the file name. Way to go, Alan. You just aced an entire paper, dude.
Why? All right. Does anyone want to read anything else, or
Oh yeah, of course. Obviously, I mean,
are we trying to crack open some Halton Arp dog, or what? We're just about to get to another good part.
I think some ARP would be some happy fun time. Yeah.
Oh yeah, Toby, bring up that ARP.
All right.
Yeah, that's
bring forward the ARP.
what's going with next?
We're about to read what's it called? Oh, let me see if I can pull this video up real quick. We can watch on radio interferometry.
Oh yeah, let's do that before this, if we're gonna do this.
So we were just reading the Sagnac experiment with electrons. That's what that paper was, yeah? Okay. Observation of the rotational phase shift of electron waves in vacuum. Okay, cool.
Up a video, or you want to play it, Toby, or I can play it? Don't matter.
Because I'm in Linux. But I haven't set that.
Dude, don't say it out loud. Shane will get all cocky.
Start
talking shit.
I just posted the PDF to the Halton ARP in the live chat for you guys if you want to pick that up too.
Are we going back to the redshift?
Yeah.
Cool. We were chapter 3, right?
Yep.
Check the live I think chat. So.
Oh, you've got that download
You're still
thing.
looking low.
Yeah.
Because your bandwidth is still being eaten, Alan.
Although, you know
what? Right.
Try it out. It actually doesn't look better now. Yeah, it actually looks fine.
When you tell
the
people
video
that
was
you're a
fine
radio
earlier
astronomer,
too.
Yeah, you really only just need to hear it because it's just a couple of images. That's nothing. If it's not too bad,
they
just
often
play it
have
through.
no idea what you mean. They know what a radio is, but maybe they get astronomy confused with astrology, and they come to the conclusion that you deliver horoscopes over the radio. This is not, in fact, what radio astronomers do. Radio astronomers use telescopes like this, or arrays of radio telescopes like this. They point it at the sky, and they collect light, which is in a very specific part of the electromagnetic spectrum. This part right at the end here with the long wavelengths. For reference, you see that little narrow.
Is it playing okay?
Yeah, it's a little fast, but they're showing us the low reds here.
Okay, no worries. I can slow it down.
Strip of visible light, that's what your eye is capable of seeing. But to look elsewhere, so to look in the radio, for example, you need to use telescopes. So we take our radio telescopes, we point them to the night sky, and we see this. This is what the sky looks like in the radio. Now, you might look at this and think, oh, yeah, I see. This is basically what the sky looks like normally, right? All the little dots are stars. And I'll stop you, and I'll say, no, you're wrong. Every single one of those dots is a radio galaxy. None of those are stars. Those blotches to the left are supernova remnants, and those big whiter blotches up here are clouds of ionized gas.
Are they now?
So I've already made one of my points, that looking in the radio opens a window to an otherwise invisible universe. Another example. This is an optical image of the M81 group, a group of galaxies in the Big Dipper. This is the same image in the radio. You get more information. The radio image tells you more than just where the stars are. It tells you where the neutral atomic hydrogen gas is, which is correlated to where the stars are, but which shows you that the galaxies are actually interacting with each other, which is a fact that you totally miss in the optical. Another example, this is an optical image of Centaurus A, a sort of ordinary-looking elliptical galaxy. But when you look in the radio, you see that there is this feature that's totally invisible in the optical. This galaxy has huge radio lobes that are being emitted from the supermassive black hole at its center.
That's exactly what ARP has been talking about.
Each of those little dots that I showed you in that picture of the radio sky is one of these radio galaxies. This is another radio image. You might have seen it before. It's the microwave cosmic background radiation, which is radiation that was emitted right after the Big Bang in its aftermath when things were beginning to cool down. It's in the radio because as the universe expanded, so did that radiation. So the radiation went to longer and longer wavelengths, and longer wavelengths is in the radio end of the spectrum. Being able to see this has totally revolutionized cosmology. It's enabled cosmologists to learn more about the early universe, learn about how the universe has evolved, learn about dark matter, and it's in the radio. So radio is the best. Another reason to observe in the radio, Earth's atmosphere actually absorbs most of the radiation coming from space. Most of the electromagnetic spectrum. So you see here, those lines that are so up at the top, that means full absorption. That light doesn't get to us at all. There are only two windows. One is in the visible, that very narrow window there, and one is in the radio, that huge window over here. Bigger window means bigger range of wavelengths, means bigger range of sources. Third, there's a technique that's unique to radio astronomy called interferometry, which allows us to get very high resolution of what we're looking at.
What?
Basically, you take a bunch of different telescopes, 27 telescopes in this case, you put them in one array, you point them all at the same object, so you're looking at that object from a bunch of different angles, and you combine that information, all those different perspectives, to make one high-resolution image. You could even put those telescopes across the whole North American continent, put one in Hawaii, put one in the Virgin Islands, and get what is called the Very Long Baseline Array, which has the resolution ability to read a newspaper in Los Angeles from New York. So, a quick recap of why radio astronomy is.
All right, cool.
Yeah,
We don't really
but
need to
for
go
all the
any further.
atmospheric problems, yeah, sure, lady.
Yeah,
What's she
it was
talking
just
about?
to give us nothing. She was just explaining what radio interferometry is and what they're doing with like radio telescopes and stuff. So the book that we're reading
And why it's
is all
the
about
best.
this.
But I mean, that's
Right.
cool. Radio interferometry, great. I mean,
Can you drop me a link to that video? Oh, you already did, didn't you?
Absolutely. I don't think so.
Yeah.
Oh,
Yeah, you
I
did
did
it.
actually.
Drop that over in my channel real quick. Yeah.
It's a good one. It's pretty quick and concise. It's like they look in the sky in a different spectrum and they see all kinds of crazy stuff. And the book that we're going over is them looking at the crazy stuff, coming up with stories about, what could have produced what they're looking what they're looking at.
hey, what mathematical abstraction do you think created that Einsteinian sky demon? Oh, that's a good one.
Exactly. So yeah, the battle for what happened with Harp is he was making observations that would falsify the stories that they're telling about what caused those lights in the sky to light up and give those readings. So, anyway, that's just to give some context to what he's doing here.
Cool. So I guess I'll start us off with this one.
No.
Oh, no, actually, Eli, have at it, man.
Go get it.
I'm gonna stand
We're in
between Eli and a book.
yeah, so we're chapter 3, right? So excess red shifts all the way down. Let's begin. There is a story about a cosmologist giving a public lecture. Afterwards, a lady stood up and said, "The real universe rests on the back of a turtle." He quickly shot back, "Well, what is the turtle standing on, young man?" Young man, replied the lady, "It's turtles all the way down." For those astronomers who are willing to consider quasars much closer than their redshift distances, there is one great stumbling block. That block is the instilled certainty that normal galaxies can only have velocity redshifts. When it comes to intrinsic redshifts in galaxies, most astronomers would consider that to be turtles all the way down. Yet we have already seen signs that quasars are not the only objects in the universe to have intrinsic redshifts. This would almost have to be the case just from considerations of continuity. There is a very obvious continuous progression of empirical characteristics from unresolved high redshift quasars through lower redshift compact objects and finally into normal galaxies. We can argue that this is simply evolution in age because the compact objects must be young, both from their tendency to expand due to the outward pressure of the concentrated energy and the fact that the high energy tends to decay unless strongly fueled. Actually, though, I was led to look for intrinsic redshifts in companions to large galaxies by an empirical series of results. The Atlas of Peculiar Galaxies contained a very interesting class of galaxies called spirals with companions, smaller galaxies. On the ends of arms, how had they got there? How had they got there? Certainly not by accidental collision or by the beginning of a merger process, which is fashionably used to explain everything in the extragalactic realm. I actually read in the Astrophysical Journal once that double galaxies are galaxies in the process of merging, and single galaxies are galaxies that have already merged. I had argued that since galaxies characteristically eject material which eventually forms new galaxies, and that if ejection took place in the galactic plane, then it would pull material out in the form of a spiral arm attached to the companion. Figure 3 1. Here is number 49 in my Atlas of Peculiar Galaxies, and it suggests quite plainly what is going on. Give me one second. I need to spit my chew out.
That image, when we get to it, it looks like an ulcer my dad had in 1972.
Anyways, whether or not that is true, I decided to look at the redshifts of the companions to see if by any chance they were systematically greater than the larger galaxy. They were, and that started another long running battle, which eventually led to a quantitative proof of the dependence of redshift on age. The clues begin in the local group of galaxies centered on our giant SB spiral M31, historically known as the Andromeda Nebula. M31 is the most massive galaxy in our group and is classified SB by virtue of its extensive central bulge of old red stars. Every major companion, by inference, including our own Milky Way galaxy, is positively redshifted, as seen from M31. The next nearest major group to us, the M81 group, is centered on the same kind of massive SB galaxy, and again, every major companion is redshifted with respect to it. By 1987, there had been a dozen different investigations, every one of which showed companion galaxies were systematically redshifted. See Table 7.1 of Quasars, Redshifts, and Controversies. By 1992, there were 18 different references to studies which showed this effect in the published literature. In spite of all of this, a paper then appeared in the Astrophysical Journal, which interpreted companion redshifts as velocities to derive masses of parent galaxies and referenced none of the 18 papers which showed that the velocity assumption was untenable. I got pretty heated up over this, and after a lengthy battle, managed to get an answering paper published in the same journal, Astrophysical Journal 430 74 1994. Figure 3 2 here is taken from that paper. One interesting development that had taken place was that a new member of the local group of galaxies had been found, IC 342. This dwarfish spiral was at low galactic latitude, figure 3 3, and an accurate absorption and distance had only been determined recently. It then became a member of the local group at about 1.2 MPC distance on the other side of M31 from us. That's parsecs, right? At plus
Yeah,
289.
actually, those are megaparsecs.
Okay. Megaparsecs. So at plus 289 kilometers a second redshift with respect to M31, it had the largest excess redshift. Actually, this redshift was very close to 4 times the basic redshift quantization of 72.4 kilometers per second, a matter that will be discussed further on. This discovery brought the count to 22 out of 22 of the major companions, all of which had higher redshifts than the dominant galaxy in the 2 best known nearest groups. The chance of this arrangement of galaxies randomly orbiting their central galaxies with equal numbers of approaching and receding velocities was only 1 in 4 million. Hmm. Hmm. Major clusters of galaxies. If companion galaxies and groups have systematically larger redshifts, what about less luminous galaxies and clusters? One could logically argue that great clusters like the local supercluster were made up of many groups like the M31 and M81 groups. In fact, it is true that if one looks at the Virgo cluster, i.e., the center of the local supercluster, one finds all the usual morphological types of galaxies. And the smaller galaxies are systematically redshifted with respect to the larger. One can see this effect in 2 ways. First, one can calculate the mean redshift of the galaxies in the Virgo cluster by weighting the redshift of each galaxy by the brightness of the galaxy. If luminosity is proportional to mass, then one gets the redshift of the average mass of the cluster, the only dynamically meaningful quantity. This calculation gives a mean redshift for the Virgo cluster of plus 863 kilometers a second. Now, the value calculated by assuming all the galaxies have the same mass comes out to between 1,000 and 1,200 kilometers a second. Why this striking difference? It is simply because the smaller galaxies have systematically higher redshifts. The second way to see this effect is to note that late type galaxies, spirals and young spirals, are systematically redshifted in clusters. Since spirals are generally less luminous than giant E's, and further, since their mass to luminosity ratios are lower, this shows in a different way that companion galaxies in clusters are systematically redshifted. The redshift of the Virgo cluster and the Hubble constant. Sometimes I think that astronomy is not so much a science as a series of scandals. You should highlight that.
He certainly has made it sound as such.
Huh. One of the most egregious is the derivation of the value of the Hubble constant from the Virgo cluster. There have been innumerable headlines about new distance determinations to the cluster in the past decades, and most recently from Space Telescope press releases. The debate swings between the long distance scale, a little more than 20 megaparsecs, and the short distance, about 16 to 17 megaparsecs. The longer distance is used by the proponents of what's that H stand for? Says
I'm not well, short distance used by proponents of H sub 0 around 80. I'm not sure.
That's the Hubble constant, isn't it?
is that what that is?
Yeah, that's Hubble zero right there, I think.
That makes
Okay.
sense.
Okay. So the longer distance is used by the proponents of Hubble constant equals 50 kilometers a second per megaparsec. The shorter distance is used by proponents of Hubble constant around 80. The latter having the drastic consequence that the universe is then younger than the oldest stars it contains, unless one brings back the cosmological constant, etc., etc. Although both sides use different mean redshifts for Virgo, ones that favor their preferred value, see Astronomy and Astrophysics 202 70 1988, neither side pays the slightest bit of attention to the fact that they both have made an elementary mistake in computing that mean. In physics, we learn to compute the center of mass of an ensemble of particles by weighting each particle. How can we compute the mean redshift of the center of mass of a cluster of galaxies without weighting the mass of the galaxies? Of course, astronomers insist on assuming that the low mass and high mass galaxies have the same average redshift. If that were so, they would get their usual answer, and they should have no objection to making the more rigorous calculation. In fact, if they define the dynamical center as the most luminous and massive galaxies, which should not drift away from the rest of the cluster, they would not be able to change the mean redshift of the cluster by adding or not adding negligibly small galaxies over which there is obvious disagreement as to membership. Another adjustment, which pushes the derived Hubble constant to higher values, is the notion that the mass of the Virgo cluster attracts our own local group, and its consequent infall velocity must be added to obtain the true cosmic recession velocity of the Virgo cluster. The infall velocity is the supposed result of the gravitational attraction of the Virgo cluster on the local group. But if masses of galaxies have been generally overestimated, or if peculiar velocities between groups are very small, both of which will be argued later, then this adjustment cannot be used to increase the Hubble constant, as in the conventional derivation. Moreover, if galaxies on the near side of the Virgo cluster were falling towards its center, then the brightest galaxies would have the more positive redshifts. The opposite is actually true. Therefore, the 1400 kilometer a second systemic redshift used for the much publicized Hubble constant calculations is far from the 863 kilometers a second actually measured. In fact, 863 kilometers a second is an overestimate because luminosities measured in red wavelengths should be used and also the spirals weighted less. Late type spiral galaxies as younger companions. From the beginning, we have noticed the excess redshift of companions around massive central galaxies which had large components of old stars. The implication was that these old stars had been around from the beginning of the group and that the smaller, younger companions had been ejected intermittently as time passed. These central galaxies had morphological types mainly of SA, SB, and giant E. The smaller companions ranged over the remaining morphological types, but featured dwarf E's, showing spectroscopic indications of an admixture of a population of stars younger than in the giant E's, and later type spirals SBBC, SC, SD, and IM. The latter types are marked by conspicuous numbers of bright young stars. These late type spirals were measured to have low masses from their rotation characteristics, and low mass to luminosity ratios indicative of relatively recently formed stars. Empirically, then, the smaller nuclear bulges and open spiral structure of the late type spirals came to mark them as lower mass, younger companion type galaxies. A special kind of supposedly high luminosity spiral, designated SCI, will be discussed later as really being of low luminosity because of large excess redshift due to its younger age. But for the purpose here of investigating the redshift behavior of companions in major clusters of galaxies, it will be useful to identify companions by their morphological classification as late type spirals. Late type spirals in major galaxy clusters. Figure 3-4 shows the excess redshift of companions as a function of their morphological type in the two nearest groups, M31 and M81. The later type spirals are clearly systematically higher redshift. Figure 3-5 shows the same diagram for the entire Virgo cluster, and the same pattern is evident. This enables us to check other major clusters as shown in figures 3-6 and 7. The end result is that the younger spirals in the nearest groups, as well as the 4 or 5 major clusters of galaxies, all show systemic positive redshifts. There seems to be no escape from this result. Interesting. Back to the Virgo cluster. In figures 3-4 and 3-5, what is really most apparent is the minimum redshift exhibited by the brightest SBs. In the Virgo cluster, galaxies of this morphological type are predominantly low or even negative redshift. One could obtain a very low redshift for the cluster if one were to accept them as the dominant galaxies in the cluster. The SOs, kind of disk galaxy without bright young stars, which are the most numerous galaxy in the cluster, actually show a continuous gradient of redshift from the brightest to the faintest. Figure 3-8 shows their apparent magnitude redshift relation. Again, one could pick almost any redshift for the Virgo cluster one wanted, depending on the apparent magnitude of the SO, which one chose to be representative of the mean mass. On the conventional assumption, the SOs are supposed to define a horizontal line in figure 3-8. In view of this uncertainty, the best procedure seems to be to make a luminosity-weighted integration over the galaxies in the cluster and hope that this averages close to the age of our own Milky Way galaxy, so that there is no age-induced differential redshift. It is encouraging to note that the plus 863 kilometer a second derived in this way is very close to the largest, brightest, and apparently oldest galaxy at the geometrical center of the Virgo cluster, M49, also known as NGC 4472. That seems the best bet to be the currently dominant galaxy, and it has a redshift of plus 822 kilometers a second. If we take the short distance scale to the Virgo cluster of 16 to 17 megaparsecs, in my opinion, the more correct one, we obtain a Hubble constant close to 50 kilometer a second per megaparsecs. We will see in Chapter 9 that this fits quantitatively with a non expanding universe in which the redshift is a measure of the age of a galaxy.
Did you say non-expanding universe?
Oh,
Somebody highlight that.
Blaspheme. Blasphemer.
We will. Oh, that goes against everything they believe in, doesn't it?
How about that?
What about the negative redshifts in Virgo, i.e., blue shifts? People often ask if intrinsic redshifts are a function of age, can there be negative redshifts? The answer is yes, it is required if the galaxy is older than we are, as we see it, aside from the local group where M31 is the parent, and we see it as negatively redshifted by negative 86 kilometers a second. There are only 6 major galaxies of negative redshift in the sky. All 6 are in the Virgo cluster and are obviously members. They are chiefly the big SAs and SBs, which we have learned to associate with the originally dominant galaxies. Hence, these are probably somewhat older than any of the galaxies in our local group and may represent the original galaxies in Virgo. It is even possible that our local group originated from them. It is touching to speculate that when we look at the Andromeda galaxy, we are looking at our parent. Perhaps in Virgo, we can gaze at our grandparents. I mean, this guy's off his rocker too, by the way, but I mean, we'll keep going. Later, we will discuss aggregates of numerous faint smudges, which are called distant galaxy clusters. But we will argue that they are generally something different from the great clusters of galaxies like to our own. Pie in the sky diagrams. An enormous amount of modern telescope time and staff is devoted to measuring redshifts of faint smudges on the sky. It is called probing the universe. So much time is consumed, in fact, that there is no time at all available to investigate the many crucial objects which disprove the assumption that redshift measures distance. How about that? So much time is consumed, in fact, that there is no time at all available to investigate the many crucial objects which disprove the assumption that redshift measures distance. Still, one has to do something with these redshifts after they are measured. What is done is an area on the sky is selected and all the available measures plotted as a function of their redshift. As an example, the plot in Figure 3-9 shows what the well-known Virgo cluster looks like. What a shock! There is a great finger of God pointing directly at us. The observer, of course, this is hastily explained as due to high orbital velocities for the galaxies in the center of the cluster, which invalidate their use as a distance criteria. Man, he's hammering on it. But it is not just the center of the cluster which shows these peculiar velocities. The whole cluster is strung out. Moreover, and this is the telling point, the brightest galaxies are preferentially at the lowest redshift. This is shown even more clearly in Figure 3-10, where the negative redshifts in Virgo can be plotted. The fainter galaxies and late type spirals trail asymmetrically away to much higher redshifts. If the elementary precaution of plotting these points in proportion to their brightness had been taken, it would have been obvious that the fainter galaxies had intrinsic redshifts. Another obvious feature of figure 3-9 is that the higher redshift tail drifts off in a different direction from the center of the Virgo cluster. That cannot be due to velocity dispersion in the center of the cluster. These must be smaller galaxies in a somewhat different part of the cluster. But with a continuity of increasing intrinsic redshift, this one feature by itself is disproof of the redshift equals velocity hypothesis. Nevertheless, region after region of the sky has been presented in journal articles and public lectures that present the fingers of God as velocity dispersions and show how the universe is made up of bubbles and voids. When people occasionally question this orgy of Swiss cheese universes, the answer is always the same. Anyone who does not believe redshifts are measures of distance is termed a psycho.
Psychoceramic artifact. I love when he waxes to the
Wow.
metaphor.
Yeah, that's a good one. That's a new one. That's for sure.
Psychoceramic. Blowing bubbles and digging voids. Considering what we know about a group or cluster of galaxies, let's look for a moment at how plotting them in a pie diagram would distort the picture. Figure 3-11 shows the large, low redshift galaxies at the center with the smaller, intrinsically redshifted galaxies distributed around them. As soon as we plot with redshift as a distance indicator, the large low redshift galaxies pull out of the center, leaving a ring or bubble. There are many ways one could elaborate on this picture. If the fainter galaxies have plunging orbits, that would elongate the ring along the line of sight. If there is a component of rotational orbiting, that would fatten the ring toward the edges. An approximate mixed velocity dispersion is shown in the right-hand panel of figure 3-11. Of course, this is all under the usual default assumption that the cluster or group is in equilibrium. One can find a variety of forms if groups of younger galaxies were moving away from the central galaxy. Since we know that the central larger galaxies have the lowest intrinsic redshifts, it will now be necessary to go back and carefully correct the inferred distributions of galaxies in different directions in the sky. Further evidence for excess redshifts of companion galaxies. Shortly after the publication of my 1994 paper on the subject of companions described earlier, I was walking past a journal rack in the library when a paper on ARP 105 caught my eye. Curious, I skimmed it and quickly ascertained that, as with so many other objects from my Atlas of Peculiar Galaxies, which were prime examples of ejection, this was also being presented as an example of collision and merger. As figure 3-12 in the color presentation on the back cover of this book testifies, this was a particularly inappropriate interpretation because it was one of Ambarzumian's finest examples of proto-galaxies being ejected, jet-like, from an active elliptical galaxy. Exactly opposite this was the counterjet, a magnificent straight plume punching through a disrupted spiral. Fritz Zwicky, after looking at this spectra of the knots in the jet, had remarked that these were the only galaxies he knew that were not resolved with the 200-inch telescope. Alan Stockton had discovered a quasar of redshift Z equals 2.2, so close to this ejecting galaxy that the chance of accidental occurrence was less than 1 in 1,000. I was about to return the paper to the stand with exasperation when I noticed that the authors had measured the redshifts of most of the companions. What they had overlooked and what leaped off the page was that they were all positively redshifted with respect to the dominant galaxy. Since the authors claimed these companions were colliding with what they termed a giant E, there was no question that they believed the galaxies they had measured were bona fide companions at the same distance as ARP 105. It did not matter whether they were orbiting the central galaxy, falling in, or being ejected outward. One should roughly expect just as many relatively plus as minus velocities on the average. As figure 3-13 reveals, all 9 of the lowest redshifts, actually 10 if one were to include the one at plus 1100 kilometer a second relative redshift, are higher than the central galaxy redshift. One had here another case, like the local and M81 groups, where the intrinsic excess redshift of the companion had overcome the smaller plus and minus velocity dispersion. One of the reasons this was a particularly satisfying confirmation was that this was a somewhat different kind of central galaxy, much rarer, caught in the act of ejecting. It had a much higher mean redshift than the more local groups that had been tested. In addition, there was an unusually large number of companions. While I was writing this result up for communication, a preprint crossed my desk. A new investigation of the Hercules cluster of galaxies had shown that in every subsection of the cluster, the late type spirals, companions, had conspicuously higher redshifts than the early type galaxies in the same sector. This was impressive because it was a detailed confirmation of the results for companions in clusters. Finally, simultaneously with the above, a student in Holland sent me one of the secondary findings in his thesis. While investigating galaxies in the Boots void, he had discovered that 78% of the companions around his galaxies had positive redshifts relative to the dominant galaxy. Figure 3-14 shows this very strong confirmation in a large sample of galaxies. Trying to publish further results. Putting all these results together, they seem to me to offer decisive proof of excess redshifts in companions. But the author, who used the companion redshifts as velocities without referencing the contrary evidence, wrote an angry letter to the editor complaining that I had been rude in my manner of pointing this out. Another pair published a rebuttal paper claiming complex orbits could explain the preponderance of positive companion redshifts. When the further evidence paper went to the referee, he suggested the interacting companions around ARP 105 belonged to another galaxy outside the pictured area. There were hints that the thesis student who found the excess companion redshifts would be in big trouble. Wow, write a thesis and get in trouble. After holding the paper for 3 months, one referee sent a Xerox from a 1902 book on celestial mechanics plus a graph showing the moon orbiting around its barycenter. Another referee said a study of weak galaxy clusters showed the largest galaxies to have the same redshift as their cluster. When I analyzed that data, the same result turned up. The brightest galaxies had negative 355 kilometer a second lower redshift. The referee replied to the editor, perhaps the author did not understand that I have rejected the paper. The editor rejected it. At a
Can't hear me. Are you listening
Dang.
now?
Dang, that's some
That's
gangsters. That's
rough.
a gangster move, dude. He was like, "Nah,
I
nah, you're
I told
mistaken.
you.
I
Nuh-uh.
yeah, yeah, I don't care at all." That's crazy, dude. These dudes are awesome. I like peer review. It's cool. Anyway, sorry, please continue.
At a conference, one of these referees gave a rather startling, for conventional beliefs, lecture on how Fourier analysis could not be trusted, and mentioned that ergodicity did not ensure that the ensemble average was equal to the time average. He said he was eager for more data on this important subject of companions. But after 4 years, this further evidence had not been published in a major journal. The only result is a stack of insulting letters from referees and editors. One thing has been accomplished, though. I now understand what should be called the statistics of nihilism. It can be reduced to a very simple axiom. No matter how many times something new has been observed, it cannot be believed until it has been observed again. I have also reduced my attitude toward this form of statistics to an axiom. No matter how bad a thing you say about it, it is not bad enough. Compact groups of galaxies. The first compact group was discovered with the Marseille telescope in 1877 by M.E. Stevens. In 1961, Margaret and Geoffrey Burbage measured redshifts of the 5 galaxies and showed they were 800, 5700, and 3 at 6700 kilometer a second. See figure 3-19. Now, the 5700 and one of the 6700 galaxies were entwined together. If redshifts were interpreted as velocity, this meant they were separating at 1000 kilometers a second. Even in conventional terms, galaxies don't move that fast. And even if they did, the chance of catching two at just the moment of collision would be very small. And of course, the gas would not keep two separate velocities. From that time forward, it should have been clear we were dealing with non velocity redshifts. But as you might suppose, the picture has become increasingly muddied with mergers, dark matter, and gravitational lenses. While any redshifts which do not fit a conventional theory are placed in the foreground or background, is there anything new? Well, an observational advance has been made by Paul Higson, who cataloged, photographed, and measured redshifts in a sample of 100 compact groups. A compact group is defined as four or more galaxies crowded together by a factor of 10 to 30 more than their local surroundings. The catalog made it possible to test the following proposition. Since compact groups are in many cases denser versions of normal groups in which companions have excess redshifts, do compact groups with a dominant galaxy have systematically redshifted companions? Figure 3-15 answers this question by showing that as the difference in apparent magnitude between the brightest and next brightest galaxies become larger, the number of positively redshifted companions becomes larger. This makes sense because if the galaxies are all the same brightness, one does not know which is dominant and the effect is untestable. But the fact that when one galaxy becomes clearly dominant, the effect emerges. This demonstrates that non velocity effects are present in the compact group galaxies, just as in every other group tested. This point is strikingly illustrated in Figure 3-16, where the distribution of companion redshifts in compact groups with the most dominant galaxies is compared to the local group. Actually, most groups have companions with up to about 800 kilometers a second higher redshift. And it is obvious that the local group is missing companions of above about 300 kilometers a second. The reason is quite simple, namely that astronomers are just unwilling to call any galaxy more than 300 kilometers a second higher than N31 a member of the local group because that makes the preponderance of positive redshifts embarrassingly obvious. If one examines the brightest galaxies as they fall on the sky, however, it is immediately apparent that there is a loose string of them running out of M31 through M33 and ending close to 3C120 near the disk of our galaxy. See Figure 8-1 in a later chapter. These galaxies have redshifts up to 900 kilometers a second and are obviously members of the local group. A group of later type spirals called the Sculptor group is located closer to us than the M81 group. As the last panel in Figure 3-16 shows, it also has higher redshift companions. Details are available in Quasars, Redshifts, and Controversies, page 131 in Journal of Astrophysics and Astronomy, India, 1987, chapter 8, page 241. An earlier study of what I called the multiply interacting galaxies comprised the most striking examples of what later came to be called the compact groups. What I pointed out in that original study was that these multiply interacting groups preferen- preferentially occurred near large, low redshift galaxies. In some cases, for example, NGC 3718, the high redshift interacting group could be seen actually bending back the spiral arms of the larger galaxy. Consult the picture on page 94 of Quasars, Redshifts, and Controversies. This result made it clear that the compact and interacting groups were just a more concentrated ensemble of young, non equilibrium companion galaxies which had been ejected more recently from the parent galaxy and were composed of material of higher redshift. Aside from being empirically true, this interpretation solves all the conventional paradoxes of the failure of the galaxies to merge into a single galaxy on a cosmic timescale. It also explains the unbearable presence of discordant redshifts. Of course, none of this is conceded by the conventional army. Well, yeah, it's hard to get a concession from them. Large excess redshifts in compact groups. We have just seen that the so-called accordant group members, defined as having redshifts different from the group by less than 1,000 kilometers a second, demonstrate again that the fainter members have the higher redshifts. But most shocking of all, there are a number of mostly fainter galaxies that fall in these compact groups which have redshifts thousands and tens of thousands of kilometers a second greater than the group figure 3-17. The consternation caused by the apparent membership of these highly discordant galaxies has led to a blizzard of papers arguing that, despite appearances, they were just projected background galaxies. Just in case, it was also argued that they were gravitationally lensed background objects. To be triply safe, it was also argued that we were seeing filaments of galaxies end on like looking down a straw with a galaxy stuck on the far end. The only trouble is that in the famous case of Seifert Sextic, the length of the straw had to be about 26,000 times its diameter. See Astrophysical Journal, 474-74, 1997. Figure 3-17,
We
however,
call
shows.
that, I'm sorry, man, but we call that coping.
Oh yeah. Major code. Yeah. I mean, we go to geos and see it right now. Figure 3-17, however, shows with small plus signs how background galaxies should increase sharply in number with increasing redshift. The numbers of discordant redshift actually decreases precipitously in this direction. It seems to me that at a glance, it is clear the discordants are not background galaxies, companion galaxies of high redshift. This is a very important link in the argument that material is ejected from large galaxies, initially with very high intrinsic redshift, and then ages and expands into compact active galaxies of moderately high redshift, and finally into normal companions with only slightly excess redshift. So far, we have shown that the extent of the evidence, which already existed, has been enormously strengthened by new evidence that normal companions belonging to dominant galaxies have excess redshifts in the hundreds of kilometers a second. Companions with excess redshifts of thousands to tens of thousands of kilometers a second establish a compelling continuity to the quasars, which start at about 20,000 kilometers a second excess redshift and go up to nearly the velocity of light, if they were really velocities. Unfortunately, there is not much in the way of new results on this group. In 1982, a list of 38 of these high redshift discordant companions was published. They were discussed in two astrophysical journal papers and in a chapter starting on page 81 of Quasars, Redshifts, and Controversies. Yet, despite the fact that almost every one of these objects is a fascinating study in itself, no further study of these key objects has been made. Certainly, these crucial discordant redshift galaxies have been deliberately avoided by the world's biggest and most expensive modern telescopes. To mention just two examples in order to re-emphasize the importance of these kinds of companions, I show in Figure 3-18 a schematic of the large active SB NGC 4151. Deep photographs of this galaxy can be seen in Quasars, Redshifts, and Controversies, page 91 and 92. We saw in Chapter 2 how this cipher was flanked by two pairs of quasar candidates and an apparent ejection cone with a strong X-ray BL lac inside this cone. But also around NGC 4151 are associated large companions with redshifts between 6,400 and 6,800 kilometers a second. Two of these companions, NGC 4156 and G1, lie at either end of the two major spiral arms. With their similar redshifts, are they not like the pairs of quasars discussed in chapters 1 and 2? With the material of the arms trailing behind them, are they not reminiscent of ejection in the plane as conjectured at the beginning of this chapter? But perhaps equally striking is the numerical value of the excess redshifts of these major companions to NGC 4151. If one refers to Figure 3-19, one sees that three galaxies in Stephan's quintet also have 6,700 kilometers a second redshift, and the three galaxies roughly on the other side of the large SB galaxy NGC 7331 have 6,300, 6,400, and 6,900 kilometers a second redshift. Galaxies come in groups, and there is no other group leader for these 6,700 kilometer a second companions to belong to other than the big galaxies at their center. In later chapters, we will show that galaxies and quasars tend to occur at certain preferred redshifts. This quantization implies that galaxies do not evolve with smoothly decreasing redshifts, but change in steps, SCI spirals, as young, low luminosity galaxies. The companion galaxy northeast of NGC 4151 has the sharply defined spiral arms which define it as an SC spiral of luminosity class 1. This highest luminosity class is assigned because these galaxies characteristically have moderately high redshifts, which are taken to indicate large distances and high luminosities. Since it is attached to the low redshift, 978 kilometers a second, NGC 4151, it in fact must have an intrinsic redshift and a low luminosity. The same is true of NGC 7319, a high redshift SCI galaxy in Stephan's quintet, which must be at the distance of the low redshift, NGC 7331, 1114 kilometers a second. See Figure 3-19. How can we check this result? There is a method of estimating distances to galaxies called the Tully-Fisher method, which uses the rotation of a galaxy to judge its mass and thus its luminosity, and then its distance by how faint it appears. Well, that's seems reliable. In Figure 3-20, we see the difference between the redshift distance and the Tully-Fisher distance plotted as a function of the supposed luminosity of the galaxy. We see that for normal spirals, the two methods are calibrated to give the same distance. But for the high luminosity spirals, SCIs, the redshift distance is too great by up to 40 megaparsecs. This huge error demonstrates that the redshifts of the SCIs are too high. A vivid illustration of how wrong astronomers' estimates of the sizes of SCI galaxies are is shown in Figure 3-21. The large galaxy is the SCI spiral NGC 309 at its supposed redshift distance. The small oval insert shows the size of one of the largest galaxies for which we know an accurate distance, M81. The giant M81 is swallowed like a knot in the arm of the unbelievably large SCI. This picture was published in the April 1991 issue of Sky and Telescope, and the professional astronomers who saw it gasped in astonishment. But the paper with the analysis was thrown out of the astronomical journal with great prejudice. When published in Astrophysics and Space Science 167 and 183, it detailed a number of other cases where SCIs could be shown to be low luminosity, intrinsically redshifted galaxies. I speculate that the sharp, well formed arms are young ejections before they have had time to be deformed and to spread out. But most astronomers are willing to suppress this observational evidence in order to protect the key assumption about extragalactic redshift from re examination. The non interacting companion to NGC 450. One case that was further investigated is the peculiar SC spiral NGC 450. Shown in Figure 3-22, it has a redshift of 1900 kilometers a second, and the apparently interacting companion has a redshift of 11,600 kilometers a second. Just at the point of interaction, there appear three enormous HII regions at the redshift of the SC galaxy. These were so gross that the expert who first spotted this system just assumed they were foreground stars. These glowing regions of excited hydrogen gas are so exceptional that I frankly cannot see how anyone with reasonable common sense and good judgment would not immediately realize that they are a result of the unusually close interaction with the companion. Nevertheless, a pair of astronomers measured some rotation curves in the system, pronounced them normal, and published a paper proclaiming non interacting in the title. There would be nothing new to report if it was not for the Spanish astronomer Mariano Moles, who had long been intrigued with the. Is that Moles or Mole? Who had long been intrigued with this system, and unknown to me, had conducted
Moles.
okay, an extremely thorough observational project, photometry, spectroscopy, and imaging on it with a moderate aperture telescope at Calar Alto. Calar Alto. His analysis demonstrated six different observational results, all of which led to the conclusion one would have to invoke an enormous conspiracy of accidents in order to avoid the conclusion that the companion is a moderately low luminosity galaxy interacting with NGC 450. One particular aspect was especially pleasing to me. It involved the circumstance that on one of my last runs on the 200-inch telescope at Palomar, I had measured the redshifts of the bright HII regions on the companion side of NGC 450. In particular, I had gone after the fourth and faintest HII regions, which was just at the end of the high redshift companion, where the companion spread out in an apparent interaction effect with the lower redshift galaxy. It was a difficult observation, and I had to use the the Oki multi-channel spectrophotometer, commonly called the Gold Cadillac. But the emission lines were strong, and I got good measures, which I reduced before leaving California for Europe. The redshift showed larger than normal differences of about 100 kilometers a second, but the faintest, near the end of the companion, showed a plus redshift of 400 kilometers a second, well in excess of escape velocity from NGC 450. That 400 kilometer a sec measure enabled a very satisfying model of the interaction to be constructed. It was simply that NGC 450 was rotating clockwise, and the companion was coming up from behind it. As the spiral arm of NGC 450 approached the companion, its gas was being pushed back and was accumulating and forming the very large HII regions. The companion, which is wedging itself in between the spiral arms of NGC 450, was close enough so that the nearest HII region was actually beginning to fall into the near end of the companion. The unexpected confirmation of this came from the hydrogen emission image, which showed a trail of excited gas as this fourth HII region fell toward the high redshift companion. See figure 3-23. The referees go ballistic. When this new paper, with 6 authors, was sent to the journal, it elicited furious rejections by 2 referees in a row. Anonymous messages such as ludicrous and bizarre conclusions based on an extreme bias of the authors wishing to find non cosmological redshifts were forwarded. One referee suggested that since we knew from the redshifts that the galaxies could not be interacting, the system should be adopted as a control for testing interaction evidence in other groups. The principal author was so appalled he considered giving up research. But by a great stroke of fortune, he asked for a third referee, who turned out to be a breath of sanity. Carefully enumerating all the ways in which this new study presented better observations than the previous ones, the last referee showed how the conclusions were properly drawn from the new data and also commented that the second referee seemed too angry to give a fair assessment of the worth of the paper.
Wow.
Jubilation.
He finally caught like a small. It just kind of stands out that one person actually stuck their neck out for once. It's crazy.
I wonder
Oh
how long he
man.
was referee.
Yeah, I'm sure it amounts to very little.
Jubilation that the paper was finally published has to be tempered with the cold experience that much fewer than 1/3 of the referees in this field are objective. Disappointing also is the fact that even though this observational paper was published in a major journal, no notice was taken of it. I relate this story in detail because I think it reveals in the most telling way what the situation is in this particular branch of science. The facts can be consulted in Astrophysical Journal 432 135 and references therein. The environs of the average bright spiral. When pressed, skeptics usually complain that the examples are selected, that they don't represent a complete sample. But when a complete sample is carried out, for example, a survey of 99 bright spiral galaxies carefully compared to non galaxy control fields, and it shows interacting and peculiar companions are significantly associated with the central bright spirals, Astrophysical Journal 2047, then the results are ignored. Not enough observing time was allocated to complete the measurements of the redshifts, but that was really not necessary, as anyone could tell by looking at the galaxies that they were medium high redshifts. An example of such a galaxy is shown in figure 3-24. The galaxy is NGC 4448, and the analysis in Astrophysical Journal 273 167 shows that the numerous peculiar faint galaxies have redshifts ranging between 5,200 and 36,000 kilometers a second, while the central galaxy is at 693 kilometers a second. Another galaxy just embedded in a dense cloud of fainter, certainly higher redshift galaxies is the starburst, dusty NGC 1808 in the southern skies. That is shown here in figure 3-25. Oh, that's beautiful. The origin of companion galaxies. The ejection of quasars from active galaxies documented in chapters 1 and 2 leads to an extraordinarily important synthesis, which I did not at first fully appreciate. It was not until after the later chapters on evolution of clusters of galaxies from clusters of quasars that I realized what the data did was to establish the origin of companion galaxies as the endpoint of the evolution of quasars. To understand how we come to this result, one must go back to 1957 when Victor and Barzoomian from just looking at galaxies on sky survey photographs, proposed that young galaxies were born from material ejected from older active galaxies. Independently, I reached the same conclusion from my Atlas of Peculiar Galaxies in 1966. By 1969, the much respected Swedish astronomer Eric Holmberg was visiting the Mount Wilson and Palomar observatories. What was that?
It's just a big cheer for Mount Wilson there. Sorry.
Oh. After 20 years of studying groups of galaxies, he was in possession of some startling evidence. Namely, that companion galaxies were preferentially distributed along the minor axis, rotation axis, of the dominant galaxy. As a young researcher at the observatories, I discussed with him and Barzoomian's evidence for linear ejection of new galaxies. My evidence for ejection of radio quasars and pairs of objects across disturbed galaxies, and my most recent evidence, 1969, that proto companions ejected in the plane of a spiral were stopped very close to the ejecting parent. He agreed that his alignment of companions along the minor axis was strong evidence for the ejection origin of companion galaxies. But he would not utter a word of this at the observatories for fear of being ridiculed. I was disappointed because I badly needed support for my findings. Sometime after he had gone back to Sweden, however, his paper appeared in his country's Archive Astronomy. To my delight, he forthrightly stated physical satellites of spiral galaxies are apparently concentrated in high local latitudes and favor systems which have blue nuclear colors and contain large amounts of gas. The results seemingly point to one interpretation that the satellites have been formed from gas ejected from the central galaxy. Italics added for emphasis. What the X ray quasar data showed in 1996 and what I did not immediately grasp was that the quasars were also preferentially ejected along the minor axis. This was first apparent in NGC 4258, where the quasars were only 13 and 17 degrees away from the minor axis. Then came NGC 4235, figure 2 5, where the pair were only 2 and 12 degrees away from the minor axis of a clearly defined Neely edge on spiral. Finally, NGC 2639, pictured here in figure 3 26, shows a group of 7 X ray sources coming out exactly along the northeast minor axis. These latter, closer sources are apparently most recently ejected. The outer pair of quasars may represent earlier ejection when the minor axis was rotated in a somewhat different position. In general, such minor axis rotation could account for the greater spread in minor axis alignment of the older companion galaxies, as summarized in Table 3 1. The fainter X ray sources coming out along the northeast minor axis of NGC 2639 contain 4 optically identified BSOs or BCGs. These blue stellar objects and compact galaxies are predicted to be less luminous, higher redshift objects on their way out of the nucleus of NGC 2639. In the naive hope that they might someday be spectroscopically observed, I give their exact positions in Table 3 2. It is not always possible to obtain cases of ejecting galaxies where the major axis, and hence the minor, is well defined. An example is NGC 1097, a barred spiral, where the position of the major axis is necessarily uncertain by about 10 degrees. See figures 2 7 through 2 9. Given this uncertainty, however, the 4 nearest quasars are within about plus or minus 20 degrees of the estimated minor axis, as noted in Table 3 1. This places them just between the long luminous optical jets which emerge from the nucleus and must represent some form of ejection. The most compelling evidence for the origin of companion galaxies is certainly their coincident alignment with quasars. Figure 3 27 shows how the quasars and companion galaxies occupy the same volume of space along the minor axis of the ejecting galaxy. Together with the smaller but systematic excess redshifts of the companions, there seems to be no alternative to the conclusion that the quasars are ejected as more recently created matter and that their intrinsic redshifts decay with time. The morphological and spectroscopic evidence shows them to be evolving into more normal galaxies. Ejection along the minor axis involves no rotational component of motion, and hence the objects remain on radial orbits as they age. It will be discussed in Chapter 8 how the intervals of quantization of the quasar redshift values also decay into the smaller quantization values observed in companion galaxies. We will discuss in Chapter 9 how the Narlikar? I don't know. ARP
You got it.
application. Narlikar ARP application of the mass creation theory predicts initially rapid ejection of low luminosity, high intrinsic redshift objects, followed by a slowing and final stop out at about 400 kiloparsecs, just the range within which quasars and companion galaxies are found. As they continue to increase in luminosity, they slowly start to fall back, roughly, if not perturbed, along the line of original ejection. They also continue to diminish in intrinsic redshift as they evolve into normal galaxies, as shown in Figure 9 3. All these properties are observed and cannot be explained on the assumptions of the Big Bang Theory. Ooh.
Whoopsie.
Ooh. Spectacular confirmation. As this book was being finished, word was received from Professor Yaquan Chu that he had measured with the Beijing telescope the new X ray candidates around the extremely active Seifert NGC 3516. Figure 11 of that Swedish journal, I think,
It's A&A.
A&A. Okay. Oh, okay. Yeah, Figure 11 of A&A 319, page 319, chapter 36, 1997, shows the X-ray map derived by ARP and Radic from the archive observations. There are 5 X-ray sources marked there, which Chu confirmed as quasars. Figure 9-7 shows their redshifts. A quick check of the minor axis direction revealed they all lay within about plus 20 and minus degrees of the minor axis. Together with the bright BL-LAC type object to the northwest, that meant 6 quasars coming out along the minor axis of this violently active Seifert, all more closely aligned than the average of the many Holmberg companions. But this did not exhaust the dynamite in Chu's observation. It turned out that the quasars were ordered with the highest redshifts closest to NGC 3516 and the smallest redshifts furthest away. Moreover, the redshifts were all very close to the quantized redshifts to be discussed in Chapter 8. I think the reader can already sense the exultation with which we receive this news. Here was an observation which fulfilled every prediction as discussed in Chapter 9, was an incontrovertible confirmation of the sum of past observations, and which we knew eventually would ensure that 30 years of struggle would be of value. Yay! They excited. Companions ejected in the plane. In the beginning of this chapter, I mentioned that it was my initial idea from studying photographs that if proto-galaxies were ejected in the plane of their originators, they would pass through a phase of being companions on the ends of spiral arms. This idea was abetted by my belief that spiral arms were the result of ejection processes and that companions on their ends were related to the large knots one often saw along spiral arms. Figure 3-1 shows a compact, luminous object emerging from the center of a galaxy, trailing material behind it. Figure 3-28 shows 2 small companion galaxies on the ends of 2 long straight arms. Both of these pictures are from the ARP Atlas of Peculiar Galaxies. This means that already in 1966, we had pictures which showed at a glance that galaxies ejected compact objects which evolved into companion galaxies. Because knots and spiral arms were usually dominated by glowing HII regions, they were presumed to be excited by hot, recently formed stars. Was there something faint of higher redshift inside that was masked by this gas of the parent galaxy? Or had the bullet passed on out, leaving star condensation to take place in the entrained gas of the galaxy, perhaps constrained in the magnetic tube of the spiral arm? To answer such the, to answer such questions required observational hard work, which was obviously not forthcoming. But the broad thrust of the observational inferences was helped by the X ray observations reported in the first two chapters. There we saw that the newly created quasars, which passed far outside the bounds of the galaxy, had a strong tendency to lie along the rotation axis, or at least not in the plane. Were they many examples where the X-ray ejection had gone off in the plane? There may be some which have not yet been recognized, but one clearly probable case was called to my attention by the Japanese astronomer Iwaki. Figure 3-29 shows the barred spiral NGC 1672. This galaxy has strong X rays coming from its Seifert nucleus, as well as X ray sources coming from two diametrically opposite points, just at the ends of its bar where the curved spiral arms begin. We know that X ray sources are ejected from the nuclei of active galaxies. What happens when they are ejected in the plane of the galaxy? Whatever their nature, they will be slowed down more going through the material in the plane than if they were ejected out of the plane. That means they will go through their rather rapid initial evolution closer to their galaxy of origin. If they evolve completely into a companion galaxy, they can then become higher redshift companions connected to or still interacting with their galaxy of origin. What do we see at the position of the two X ray sources in NGC 1672? Not much on routine low resolution images, just the high surface brightness of the bar. But galaxies typically contain a lot of obscuring dust in the plane, particularly barred spirals that often have thick lengths of dust running out along the bar. See picture of NGC 1097 in Figure 2-9. The Japanese satellite telescope ASCA, which detects higher energy X rays, registers the Western source much stronger than the lower energy X rays of ROSAT. This implies very strong dust absorption. If there were a highly obscured BL-LAC object at the position of X3 in Figure 3-29, how would we detect it? Even with advanced infrared equipment on large aperture telescopes, we could have trouble identifying a faint object and getting a definitive spectrum. But that is not to say we should not try. Eventually, we should succeed in identifying what those strong X ray sources are. Another example of what I would take to be ejection from the plane is shown in Figure 3-30. The Space Telescope photograph of the Seifert 2 galaxy, marked 573, shows a pair of radio sources ejected in opposite directions from a radio nucleus. Hydrogen alpha gas seems to form bow shocks around these ejected sources, bow shocks. But material from the galaxy is clearly drawn out in these ejections. It almost never happened. As important as I believe the intrinsically redshifted companion galaxies are to understanding the nature of cosmic redshifts, I must recall that I almost did not have the chance to publish or to follow up the implications. It was 1967, and I had just finished the Atlas of Peculiar Galaxies. I had used my staff members' observing time to study the best examples of companions on the ends of spiral arms, and I submitted a paper, the abstract of which is reproduced above. It was well understood at that time that the journal in which important papers were published was the Astrophysical Journal. The longtime editor of that journal was Subramanian Chandrasekhar.
Subramanian Chandrasekhar.
Oh, yeah, I did pretty good. A theoretician of great renown and generally considered a tough but fair guardian of its reputation. I don't know now how I ever could have imagined that he would have been pleased by these interesting new observational results. He returned the paper with a handwritten message scrawled across the top. This exceeds my experience. It took a little while for it to penetrate my stunned senses that he had rejected the paper without ever sending it to a referee. I suddenly felt a cold shudder of apprehension as I realized that my prospects in astronomy were not very bright if I had alienated the editor of the Astrophysical Journal. What to do? First, I felt I had to safeguard the observations by getting them published somewhere they could be read and referenced. The only possibility seemed to be the journal that was just starting up called Astronomy and Astrophysics. With some trepidation, I submitted the paper there. After some anxious weeks, the paper came back. A new jolt of panic hit when I saw it had been refereed by another renowned and conservative astronomer, Jan Oort. Forcing myself to read on, I was overjoyed to find that, although he did not agree with the interpretation, he found the observations valuable and interesting and accepted the paper for publication. In the ensuing years, I came to know Ort better and found him to be an extraordinarily polite and gracious man. Underneath, however, he had opinions of steel and apparently would never for a moment entertain a solution which violated the usual assumptions of astronomy. Many years later, when he was nearing 90, after a warm dinner at his house, he wrote me a letter urging me to give up my radical ideas and once again participate in the privilege of doing mainstream astronomy. I thanked him and answered him with a quote from my wife: "If you are wrong, it doesn't make any difference. If you are right, it is enormously important." A most vivid memory I have, however, comes from the time I was sitting next to Ort in the Krakow meeting of the International Astronomical Union. Uh, Ambarzumian was chairing the session, and Ort leaned over to me and whispered, "You know, Ambarzumian was right about absolutely everything." Many times since then, I have wondered whether if Ort had said that out loud and backed it with his enormous influence, the paradigm of astronomy today might not be much different. And I wondered, too, whether this was not his real intuitive intelligence slipping for an instant out from behind the secure conformity of accepted dogma. At any rate, although it pained him very much to see an interpretation given which was contrary to his own, it never occurred to him to prevent another genuine observer from speaking or publishing that opinion. To say that this was the ethics of an old fashioned gentleman is to emphasize that ethics have changed today. Mhm. But that did not solve my problem with the Astrophysical Journal. The director of the Wilson and Palomar observatories called me down to his office. To my horror, there was a copy of my paper sitting on his desk. Chandrasekhar had sent him a copy of my paper complaining that I had been caught up in phantasmagoria. Who could my who could forget that word? And suggested that my director do something about it. He did. He told me that my appointment would not be renewed next year. Stunned disbelief and fright was my reaction. My understanding was that, though unwritten, my tenure at the observatories was permanent. And yet, what could I do if it were not? I could only mutter weakly that I would wait for his notification in writing. As the weeks and then months went by with no letter arriving, my terror began to subside and I began to think the crisis had passed. But I felt hunted, and there loomed the question of how I would handle the publishing of future observations. In the height of the storm, there seemed only one principle to cling to. That was fairness. I knew the observations were good and the interpretation was based on scientific reasoning. The Astrophysical Journal had a responsibility to communicate them to other astronomers. Even though it would exacerbate my position, I decided I must protest to the editorial board. Almost a year passed, and one day I heard that Chandrasekhar, after long and honorable service, had decided finally to relinquish the onerous burden of the editorship of the Astrophysical Journal. By then, I was concentrating on further observational programs, and I remember thinking, well, it is a hard job, and he has been at it a long time. I suppose this had to come sooner or later. A few months after that, I came down to the Friday afternoon astronomy luncheon at Caltech. There was a seat open next to Fred Hoyle at the middle of the long table. I sat down next to him and started chatting happily about new observations. After a while, Chandrasekhar, there on a brief unannounced visit, slowly entered the room and proceeded to the only empty seat at the table, directly opposite me. After finishing the subject with Fred, I found myself looking directly across at a silent Chandrasekhar. Merely to make polite conversation, I remarked, "You must be enjoying the respite from your arduous duties as editor." Suddenly, there was one of those complete silences. As all conversation stopped and the whole long table turned to stare directly at us, Chandra rose up a few inches from his chair and said angrily, "How could I continue to be editor when people like you complained about me?" I was stricken with embarrassment, but for the first time before or since, managed to come up with an immediate reply. I would hope, in spite of our professional differences, to remain cordial in public. The table went back to conversation and we did not speak to each other for the rest of the meal. Come to think of it, we have never had an occasion to speak since then. In fact, these were the only words we spoke to each other in our entire lives. Of course, Chandrasekhar went on to be awarded the Nobel Prize for his work on structure of stellar interiors in allied subjects. About that time, I was at an astronomical meeting and attended a lecture he gave. I was amazed that he spent a great part of the lecture talking about his relationship with his erstwhile teacher, Sir Arthur Eddington. In those remarks, Chandrasekhar stressed the emotional hurt that he had received when Eddington had strongly rejected his ideas on the degenerate cores of white dwarf stars. Dwarf stars. He emphasized what a debilitating effect it had on his outlook for a long time afterward. I was surprised, but I admired being able to talk about it publicly. Although at the same time, it was sad to realize that he had then turned around and passed on a similar blow to someone else. Right.
Sounds about
A
right.
chance. Yeah.
You're in the stretch.
We're close. A chance galaxy. One day I was passing the photographic laboratories at the European Southern Observatory and I saw a pile of photographs they were discarding. I picked out the object shown in figure 3-31. It turned out to be an object in the ESO catalog of southern galaxies, ESO 161 IG24. Just a chance galaxy, but it is so eloquent. 3 spiral arms with a companion on the end of each arm. And what is more, the longest arm has a series of large knots along it, which look simply like nascent companions. Of course, it would be fun to examine this system with high resolution and spectra, but is it really necessary in a broader sense? The 2 major companions are obviously not falling in, and from what we know about ejection in many other galaxies, it is just inviting us to fill in the evolutionary links. Someone who knows galaxies will someday identify and observe it. Meanwhile, we can move on to investigate the questions of fundamental physical processes. Yay!
Wow. Yo, nice job with that chapter, man. That was awesome.
Crushed it, bro.
Yeah,
And
I'm a
go
get some
ahead.
water now.
Yeah, I bet. That's crazy, man. This just feels so similar to nowadays, and I mean, the dude might as well, with the way he was treated, might as well have been a flat earther. And they do not like whatever. They never like anything he has to say ever. Crazy. Yeah. Thanks,
I was
Eli.
hoping he was going to make editor.
Yeah, sure.
That would have been the ultimate punchline, is that Chandrasekhar handed it down to him. Like, okay.
If only. Well, cool. I think we can wrap it up on that note. That was great, Eli. Anyone else have any final parting words or thoughts or anything about the paper we read, videos we watched, or about ARP? Well, all right then. So yeah, thanks everyone for tuning in. We'll go ahead and wrap it up here and close out streams. Again, this was reading night, but tomorrow night you should join us. We have Dr. Robert Bennett coming back to present part 2 of the Hildegard geocentric model, or he calls himself a geostatist, as in the Earth is geostatic. So yeah, he'll be coming to give part 2 of that, talking about ether winds, talking about the Hildegard's conception of the universe. So yeah, come check that out for sure. Highly recommend all of Bennett's presentations. And other than that, take care of yourself, everybody, and have a wonderful, wonderful
Oh,
night.
wait. Hold on one second. We got a watch party on Wednesday. Shane is debating Ruhif on curvature, Earth curvature versus optical curvature, right? The debate we've all been waiting for. When you look through a theodolite, is what you're looking at Earth curvature, or is it just an illusion based off of the curvature of the lens? Who knows? But there is a mathematical equivalence. So they're going to get into that. And then Thursday, we'll be doing our weekly Twitter space.
Boom. So there you go. So yeah, we'll see you guys for those. And yeah, take care, everybody.
Yep. And Shane's event, one second. Let me get the time for you real quick. We close out.
Oh yeah,
She's
and tomorrow
event
Tuesday nights is at 8 p.m. So that's tomorrow night 8 p.m.
Jane is 6
So
Eastern.
Yep. Thank you, sir. 6 p.m. Eastern. We'll have a watch party on Discord. It's going to be on Jaronism's show. So we'll watch it here on Discord. All right. Thank you.
Yeah, see you guys tomorrow at 8 p.m. Eastern.